there's a lot of words in this title, and I hope by the end of it, it'll be perfectly clear why compositionality, why convolutional sparse coding, why resonator networks, and all of this. This is joint work with myself, Sonia, Annabelle, who's also here, and then Dennis and Bruno. And we're from the Redwood Center for Theoretical Neuroscience at UC Berkeley. Part of our goals at a high level are to reverse engineer the kinds of algorithms that we think that the brain is using in order to be able to build more intelligent kinds of systems that are able to leverage those kinds of principles and algorithms. And so we hope to have further conversations with you all about how possibly to take these algorithms and implement them more specifically on neuromorphic devices. So firstly, I just want to introduce this problem of factorization, which we view as a central kind of problem for visual perception. So we've heard a lot of great talks and conversations about how in order to maybe advance neuromorphic computing or to be able to avoid the kinds of bottlenecks that we're often facing with big data, we need compact and efficient ways to solve these kind of combinatorial search problems that come across in everyday life. For example, the kinds of images that you're viewing right now, or the kinds of, just in terms of the pixels, are probably completely new. You've never seen them before, but you can recognize different people or different objects in a visual scene because you have an understanding of their parts. So this is the understanding or the idea of compositionality, which is that we can express a large combinatorial structure. You can think of language as another example, by being able to decompose these different kinds of objects into different parts. So an everyday example of this that you may be familiar with is the checkerboard illusion, in which P and R, they're the same pixel value, but they look perceptually different to us because we're able to factorize the reflectance of the object, so its surface properties, from the lighting of the particular environment. Or yet another example is that the world might seem perfectly still to us, even though our eyes are jittering and moving all of the time. And so we need an efficient algorithm to be able to not just use this motion from eye motion movements, not just as a bug, but actually this paper by Anderson et al. Showed that it's a feature in allowing for better perceptual acuity than you would have from just simply kind of static images. And finally, we'll be focusing on the third case, which are these what and where cases of factorization. This is a classic kind of case, and you can think of it as roughly mapping onto the two extremes for dorsal and ventral visual streams of processing, which is like decades-long standing research in neuroscience and visual neuroscience. And so then our problem statement is simply that given an image containing one or more objects, how can we return each object's identity and position in the image in a neuromorphic and efficient way? It should be noted that in this kind of problem, a brute force approach in which we try every possible combination and see if it works will return the correct solution. It simply won't do so in a tractable period of time. And so the approach that we take is to say, okay, we know that the brute force solution is not feasible or not amenable to many kinds of real world scenarios or situations. And rather, we want to understand what might be the principles at play. And so to do this, or to address this kind of question, this is where, firstly, we take a possible image. In this case, we're using MNIST as a playground data set, converting it to a convolutional sparse code. So we'll explain what that is. Then converting it to this high dimensional representation. So this is part of hyperdimensional computing, vector symbolic architectures underneath this kind of framework, because it allows for this modeling of a compositional representation. And then finally, using the resonator network as a way of disentangling horizontal position, vertical position, and object identity, in this case, one object at a time. And so now let's talk about the sparse coding part of it. You might have heard about sparse coding before, but if you haven't, then let me be the first to introduce you to it. So the idea is to understand how the brain, or in particular primary visual cortex, might be encoding natural images. And there's a longstanding degree of work in trying to analyze the receptive fields of what are called simple cells in primary visual cortex. And the experimental finding is that the response properties of these simple cells often seem to be localized, so to particular features of an image, and then these bandpass kind of filters, sort of like wavelets. And so this is the hallmark of simple cells. And one possible account of this is the sparse coding approach, in which if you train a simple model to, say, represent images according to a common set of basis functions phi, and then express individual images by changing these different coefficients A in a way that reconstructs the image, but does so in a sparse way. There might be multiple reconstructions that have the exact same image reconstruction loss, but they're going to differ in terms of their sparsity loss. And what's found is that when training this kind of algorithm, the phis are going to be returning these basis functions that look very similar to the kinds that you see in visual cortex. And so the simple way of representing this model is it's a superposition of these different basis functions, plus a small amount of noise that just accounts for residual information that can't be accounted for strictly with those kinds of components. So we think that this is a good starting point for how to first represent images, but we want a little bit more structure than just saying sparse coding. So for one thing, you can notice that a lot of the different elements or these basis functions, the phis, look quite similar to each other. They might look like just rotated or translated versions of each other. And so we want a way of representing images that's more compact. And that's where convolutional sparse coding comes in. So the idea now is that we replace the small a in here with a big A, which just means that now you can think of it as a 2D feature map of activity. We want those 2D feature maps to be sparse. And now our phis are roughly going to be the same, except we're going to learn it in this convolutional basis. So similar to a convolutional neural network, where we can reduce the complexity by making this assumption that we have the same kinds of basis functions in different parts of the image, we're going to do the same thing here. And so we can work with a smaller effective amount of phis in order to express a particular image. So this is just a kind of schematic explanation of how these images are represented. And then, so we take a feature map, convolve it by each of these features, and then this is sufficient to represent an image. So it's just a kind of special case of convolutional of sparse coding that is a little bit easier in our case to be working with. And so now we get to the hyperdimensional computing part. And like I said, the main reason or motivation for this is to be able to understand compositionality in images. So you can think roughly of the sparse coding layer as understanding the parts of an image. And this hyperdimensional computing idea is to say, okay, how can we create a structure in which those parts can be expressed into wholes? Because different digits, for example, in MNIST might have similar parts, but it's the way that those parts are configured that are what matters. And so here, this is the crash course, the hyperdimensional computing, which also goes by many other names, and as a compositional grammar that implements distributed representations. So the key things are that symbols are often mapped to random high-dimensional vectors. And the reason for high-dimensional vectors is that, and random high-dimensional vectors, is that with high probability, you can express many more things than you would if you just had a one-hot code, for example, that represented each of these individual structures. And so it allows you to create rich structures from initial random kind of primitives that correspond to, in this case, symbolic entities. So then there's binding or bundling operations, firstly, which usually corresponds to addition, which is useful for creating set representations. So if you had a vector for Alice and Bob, you could add those vectors together to create Alice plus Bob. Or association vectors, which are binding, which you can think of as akin to a multiplication operation. So if you had this since Alice saw Bob, you can represent it as a triplet of tuples. So that's Alice and subject, saw and verb, and Bob and object. And I just want to point out that the reason why you're doing this kind of separation is so that you can represent it as a different sentence than Bob saw Alice, where there's different bindings between the different variables. And then finally, you have a rule for comparing vectors, which is a similarity metric. So for vectors, this is simple. This is just going to be the inner product. And there's also permutations that are being often used in these kinds of architectures, but we're not using them in this particular case. And so the choice of HD vector that we're going to use are called Fourier holographic reduced representations. They stem from Tony Plate's PhD thesis. So the idea is the vectors are complex phasors. So a complex number is nothing but an amplitude and a phase. And if the amplitude is set to 1 for all of these elements, then it's just the phase that matters. The bundling is by element-wise addition, binding by element-wise multiplication, or also known as Hadamard product, and then similarity is just by normalized inner product. So it scales between 0 and 1. And then, so far I've just introduced it in terms of symbols, but if you want to represent numbers in which there's numerical relationships between the variables, you can start off with a random vector z that's composed of these phasors, multiply or bind it to itself x number of times. And because multiplication of phasors corresponds to adding their arguments together, you can think of that roughly as a kind of exponentiation that's going to result in another phasor variable. And so what this is just to show is if you had a toy vector with just 5 dimensions and they're spinning their phases around as you're changing this particular value of x, you're getting a different representation value for each of these random spins. And in certain cases, you can also guarantee that these different numerical entities at this integer spacing are going to be orthogonal to each other as well. But the key thing is that there's this algebraic relationship between them, namely that if you have z of x1 and z of x2 and then bind them together, that binding operation is performing a mathematical operation on x1 plus x2. And so you can perform the encodings in this distributed space or perform operations on them directly without needing to do decoding and then re-encoding back. So now we get into the details of, okay, how do we get to this high dimensional vector? And the basic idea is that after we've gotten the convolutional sparse code, we have the particular features that we want to encode, and we have the feature map. So this is indexed convolutional sparse code. This is the feature map J, and this is the coordinate XY. So this is a scalar. We're going to multiply that by this vector, which is composed by the bindings of 3 vectors. In this case, it's a random vector for the basis function J, which is the convolutional feature channel that corresponds to this element, and then the position vectors for X and Y based on some additional random seed vectors H and V. So this is using, this is a very quick introduction to all the machinery of hyperdimensional computing, but I want to be pretty thorough about the exact methods that we're using, and I'm happy to clarify more if there are kind of questions. And what we'll do is compare this to understand the benefits of a convolutional sparse code compared to a pixel encoding, in which rather than do convolutional sparse coding, we can just work off of the image pixel values together. Then in this case, for a gray image, it would just be one kind of channel, and then bind these position values together. And so we note that this pixel kind of encoding has been used in other kinds of papers before. For example, this one by Alpha Renner and colleagues. And we should note that this is a very kind of simplified version of the kind of pixel encoding that they're doing. We do this to kind of compare one-to-one the benefits of the pixel code versus the convolutional sparse code. But we think that there's a lot of really interesting experiments that they do with color and rotation and scaling and other things as well. So if you end up liking the ideas in this talk, you might enjoy that, reading through that kind of paper on arXiv as well. And so now, okay. What's the point of explaining all of that? It's to say that now we can represent the objects and positions in this HD or VSA kind of encoding as a factorization problem. So this means that if we have an object template, which corresponds to digit 3, for example, and then we shift it by a certain amount, in this case by binding vectors in this HD computing space, then that corresponds to a shifted version of this particular object template that we have. And then if we want to add in another object, that's okay. We just do that mathematically via adding it. So the nice thing now is that we have a compositional generative model for different visual scenes that, even though it's relatively simple in terms of its operations and in terms of the encoding methods, it's very powerful in explaining many different kinds of classes of images. But now this is just the encoding problem. We still have the decoding problem of understanding how the brain is able to retrieve these kinds of representations. And this is where the Resonator network is going to be coming in as a way of addressing this kind of problem. So remember, if we have this input and we go through the work of converting it to a convolutional sparse code, and the end result is this vector z, then in the end, we want to have an estimate for these different factors, h, v, and o. So these 3 problems, these 3 factors, which are the output of our particular solution. So the way the Resonator network does this is it's a recurrent neural network where its updates for h, for example, are based off of the input z, but also on the other estimates for these factors v and o. So the high-level intuition for this is that once the Resonator converges to a fixed point, then because the fixed points that we're explicitly programming into this network are going to be solutions to a good factorization of this problem, it allows us to recover the individual components of this scene, in this case, one object at a time. So I'm going to show you an animation in the next slide, but just to kind of orient yourself to what's going on here, this is just what the Resonator is visualizing for one object per at a time. These are different factors, so digit, x position, and y position. And then this is the similarity of its estimate for one of these factors over time. So the way to read this is from top down. This is at iteration 0, and then this is at iteration roughly 50. So you can kind of see at the beginning, now it settles to a particular solution, but then in between, it sort of is guessing around or looking around the space until it settles to a particular digit. So at first, there's a little bit of uncertainty as to which factor is exactly being discovered or uncovered. But then at a time, it settles to a fixed point. And then because you can measure the convergence to a particular fixed point, you can see that it's going to be settling in a particular case. And this is an example what's searching in superposition. So another kind of classical algorithm for this is a map-seeking circuit, in which you're summing multiple guesses at a time for multiple different horizontal, vertical, and object positions, and then culling these situations. So gradually winnowing down your solution space until at most one remains. And I believe David Airthorne presented map-seeking circuits at NICE about a decade ago. Resonator networks are doing a similar kind of algorithm, but one, they're operating with this HD computing kind of framework. And then in addition to that, the idea is instead of culling, the principle of self-consistency. So you want to look for correct explanations, and those are programmed as fixed points of the dynamics. So then you can tell if your particular solution is correct. And there's also been some related work on resonator networks for image factorization, so either by direct encoding of the pixels or by using a neural network to compute some of these representations. But none of this before has been used with unsupervised learning and convolutional sparse coding. And now Sonia will tell you about some of the benefits of the sparse coding approach.
Okay, so now I'm going to present the more experimental side of our work. What we wanted to do is quantify the ability of this model to factorize images into which objects are present in the image and at which position. And what we did is pick black square images and randomly place objects taken from different data sets at random positions and quantify how good the model is at factorizing the identity at the position. Today, I'm going to talk about the result on the MNIST dataset, but we also looked at results on other datasets and obtained similar results. We have many metrics to evaluate our model I'm going to talk about later. And we fixed the Resonator network hyperparameters in order to do a fair comparison to models that only does pixel encoding while we do this sparse coding extraction. So here are two main experiments that we did. The first one is looking at the scaling of the method to the search space size. One way of doing this is increasing the size of this black image in which we put the digit. And this increases the number of possible X and Y positions for the digits, which scales quadratically with the size of the search space. And in the case of MNIST, the search space is 10 times L squared because there are 10 different digits. And the bigger the search space, the harder the factorization problem is. And the second experiment we did is increasing the number of objects that are present in the scene. This introduces two different kinds of problems for the factorization. The first one is the fact that there can be pixel overlap between the digits, which is something that the Resonator, as we will see, is good at disentangling. And the second one is the crosstalk noise that is introduced by the fact that the more information we try to encode in one HD vector, the harder it is to factorize with a Resonator. So here are the results in terms of the accuracy of the factorization and the number of iterations it took for the Resonator to converge to the fixed point. The x-axis is the number of X and Y possible positions in the image, so the size of the image. And our model is the blue line, and we compare it to the model where the pixels are directly encoded as HD vectors, and so where there is no convolutional sparse code step. And here what's important is that we fixed the HD dimension, and we could always boost these results by picking a higher dimension. But here we wanted to show that adding this convolutional sparse code step helps for the same number of dimensions to get a much higher accuracy level, and this for a fewer number of Resonator iterations. And here are the results for the multi-object scene decomposition. So as Chris explained, we know in advance how many objects are in the scene, and we run the Resonator as many times as there are objects in the scene. And at each iteration, the Resonator converges to one object, which is then subtracted from the scene. And again, we obtain better results with this convolutional sparse code step. And this is because this convolutional sparse code step is an efficient and compact representation of the image structures. And we can then adapted to encode images as HD vectors, because in HD vectors we want to encode as efficient representation as we can, so that it's easier to factorize. And in the case of the direct pixel encoding, there is a lot of redundancy in the pixels, and that's why it's having a harder time factorizing the scene. So now the question is, what happens in the case where the resonator doesn't converge to the right solution? And to see, to explain what happens, we introduce this confidence metric, which measures how confident the resonator is of its answer. On the left, we see the resonator dynamics in the case where the resonator is correct. And as Chris explained, time goes from up to down. And the yellow straight line points to the answer the resonator gives. So here it returns the answer that the digit 2 is present in the image. And when it's correct, it's very sure of its answer. There is only one bold straight line, and the other columns are black. But when it's not correct, it's not as sure of its answer. And here, the two last columns are equally bright, and this indicates that it's confused between two possible answers. So the confidence metric we introduced is the difference between the two. It's something that can be calculated at each iteration for each code book, and it's a difference between the two maximal similarity values that are in color here, and then it's normalized between 0 and 1. So high confidence would be 1 and means that the resonator is correct, and low confidence is 0 and the resonator is incorrect. And we experimentally observed that the confidence is highly correlated with the correctness of the resonator, which is shown on the right. So we used this confidence metric to perform early stopping on the resonator. On the resonator dynamics, there are two different phases. There is an exploration stage, which is the beginning here, where the confidence levels are random. And at some point, the resonator lands on the right solution and converges to the fixed point of the dynamics. And we observe that when the confidence crosses a certain threshold, it will converge to the right solution with high probability. So we can stop the dynamics there and return the current guess for the resonator. And this is what we did. And we found that it's a good criterion for early stopping. We obtained no decrease in accuracy and fewer iterations for the resonator. And we find that this early stopping criterion has even larger benefits for this commercial sparse encoding method than for the direct encoding of pixels. So there are a few directions that are possible now. First, we would like to work on a neuromorphic implementation of this model. We would like to base our work on previous work, encoding sparse coding and resonators on neuromorphic hardware. We would also like to see if the method scales to other kinds of scenes or variations by, for example, introducing color or looking at times and videos. And explore other resonator extensions. For example, Chris has some work on introducing residue number systems to represent the position in the images, which introduce a lot of benefits. Also, we could introduce nonlinearities in the resonator dynamics and look at other kinds of transformations, such as rotation and scaling. So the main takeaway of this project is the fact that we built a neuromorphic model that is efficient for image factorization. It's explicitly compositional through this a hyperdimensional encoding because all images are constructed from a very small number of codebook entries and operations. It's transparent because we explicitly extract the structure of the images with this convolutional sparse code. And we introduced this confidence metric for faster convergence and resonator explainability. So this could be a model that could help visual scene analysis for neuromorphic computing. Thank you.